Problems of chapter 11, they are given in this file. So let's start with problem 14 in chapter 11. A conical pendulum consists of a bob of mass m in motion in a circular path in horizontal plane as shown in this figure, the figure 11.14. During the motion, the supporting wire of length L maintains the constant angle theta with the vertical. Show that the magnitude of the angular momentum of the bob about the center of the circle is given by L equals to square root of m squared g L to the power 3 sine theta to the power 4 divided by cosine theta. So we have a bob that is attached to a string, and the string is in turn attached to the ceiling. وهالبوب هي عم تعمل a circular motion about the center, about the one point along this vertical axis. بشكل انه الثeta عم بضل constant. This theta is the angle ما بين string وما بين vertical line. We have to show that the angular momentum of the bob is given by this expression. So let's move to the whiteboard. So فإذن let me share the whiteboard. So here it is. So هي الرسمة اللي قلنا. We have the bob, هيدا string. The length of the string is given by L, small l. وفي عنا الثeta هو the angle between the string and the vertical line. Okay? مطلوب مننا نجيب the angular momentum of the bob. So the bob is considered as a particle. It doesn't have a particular shape. And so we know what is the definition of the angular momentum of a particle. So احنا مطلوب مننا نجيب فأذن the angular momentum. وطبعا هو حدد لنا about what point. هو قالنا about the center of the circle, which is very important information مثل ما شفنا بالcourse. انه we always determine and measure the angular momentum with respect to a given point. فاذا احنا عم نجيب ال L with respect to O. And we know the definition للangular momentum هي تتذكروها هي R cross P اللي هو ال vector position of the particle R vector product مع ال linear momentum of the particle اللي هو MV. Okay? So let's actually draw all these vectors على الرسمة لحتى نشوف شو حيطلع معنا. أول شيء ال vector position of the particle, it's drawn with respect to the origin. والorigin هو center of the circle. So this is the vector R that we are talking about. And the velocity of the bob, it's quite easy to determine لأنه أنتم كلكم بتعرفوا إذا عندنا particle that is moving on a circular path, the linear velocity of this particle is tangent to the circle. فنقول إنه هالparticle عم تبرم بهالاتجاه هيدا، فإذا ال V هي tangent على الcircle، وبالتالي ال V is given by this vector. Okay? So مطلوب منا نجيب فإذا هو الماgnitude للangular momentum. So we can write down L as equal to the magnitude of R, which is R, times the magnitude of MV multiplied by sine of the angle between R and V. بما انه هون البارتيكل عم تعمل circular path, it's moving along a circular path, and the speed is defined by the vector tangent to the circle at any point, then V is always perpendicular to the vector position R, اللي هو radius of the circle, and so the angle between V and R is all the time equals to pi over 2, equals pi over 2. Sine pi over 2 is equal to 1, so therefore L is equal to R multiplied by M multiplied by V. Okay, that sounds great. Now, the point is that نحن ما بنعرف شو هي ال R. ال R منا variable عطونا إياها بالgiven. So لهالسبب لازم نروح نجيبها. We have to determine R in terms of the variables that we have in the given. نحن ال variables الوحيدين اللي بنعرفهم بالgiven هن عبارة عن variables M اللي هي mass of the particle, the angle theta between the string and the vertical line, and we have the length of the wire اللي هي L. So we have to express R كمان ال V as a function of these variables that we know اللي هن m, theta and l. So let's do it. Okay, let's start first with the r. إذا بتطلعوا على هالرسمة طلع معكم هيدا التريانجل. So let's express r as a function of r as a function of known variables. لازم يكونوا as function of L theta لأنه ال M has nothing to do with R. إذا بتطلعوا على الرسمة في عندكم هيدا triangle اللي هو فيه ال R, this is L, and this is theta. So you can immediately recognize that sine theta is defined by R over L. And so we can express R as a function of L and theta as R equals to L multiplied by sine theta. So هيدا أول variable موجودة بالangular momentum اللي كانت unknown صارت هلا known. It's a function of L and theta. But still we have to determine what is V, right? So now we have also to determine V as a function of V as a function of M, L and theta. Okay? طيب شو الطريقة لحتى نقدر نجيب V? V is the speed of the particle. نحن بنعرف إنه هون the bob it's moving along a circle. So definitely it should have a radial acceleration أو centripetal acceleration مثل ما نحن بنعرفها. وبنعرف إنه centripetal acceleration هي always it's a function of the speed. هي v squared divided by r where r is the radius. So if we get access to AC then we can determine what is v. وكيف نقدر نعمل access على ال AC من خلال Newton's second law. So this is why let's apply Newton's second law on the bob. Newton's second law on the bob in order to access the speed v. Okay. Let me draw the figure. So what are the forces acting on the bob? We have the following. So we have mg along the vertical direction. Let's call it mg. And the only other force that is acting on the bob هي the tension in the wire, which we can call T. And as we know, this is the angle theta between the wire and the vertical line. And we know, of course, since this particle or this bob is moving along the circle, that at any time it has a centripetal acceleration given by a C or a R. Doesn't matter. So let's call it AC, for example. Okay. And so now if we apply Newton's second law, then we know that the sum of F is equal to M times A. But in order to apply this, equation, we have to choose two axes two axes, X and Y, along which we are going to make the projections. So let's choose one of these axes to be the axis, centripetal axis, اللي هو radial direction. والثانية خلينا نلاقيها بشكل مثل ما صرنا نعرف هلا انه تكون perpendicular على الاكس on one side and also لازم تكون perpendicular وكمان لازم تكون تحمل الفورسز. So this is why we take the x-axis pointing upwards, okay? And now let's make the projection. So we can say sum of x equals max, right? So we can write down لأنه هون ال t عندها projection على 2 ل x وال y لأنه هذا الانجل هو نفسه هون الانجل ثيتا. So we end up with plus t or plus t sine theta is equal to m. x هي نفسها ال centripetal acceleration. So it's equal to m times v squared over r, where r is the radius of the circle along which the particle is moving. So we end up with t sine theta is equal to mv squared over r. And if we make the projection along the y-axis, sum of fy is equal to m ay. So we end up with plus t cosine theta minus mg is equal to 0. Equal to 0 because there is no motion along the y-axis. The bob, it's only moving in the horizontal plane. هو قال لي هيدا الشيء. قالنا the bob is moving in a circular path in a horizontal plane as shown in the figure. So there is no motion along the y-axis vertically. وبالتالي صار في عنا two equations. أول equation هي T sin theta equals to mv squared over r اللي هي equation number 1 و T cosine theta equals mg اللي هي equation number 2. اوكي سو نحن ما ننسى شو الهدف انه نجيب ال v squared، هدف انه نجيب ال v. So this is why let's determine what is v squared. These 1 and 2 equations 1 and 2 بيعطونا الشيء التالي v squared is equal to t times r times sine theta, so it's r multiplied by t multiplied by sine theta divided by m, right? That sounds great. So في عنا ال m is known, theta is known, ال r صرنا بنعرف شو هي ال equal ل l times sine theta, بس still ال t ما بنعرف شو هي, so we have to determine it. بس من ال equation number 2 نعرف إنه t equals ال mg divided by cosine theta. صرنا نحط كل شيء بقيمته بيطلع معنا. ال r قلنا هي عبارة عن l times sine theta, right? حتى over m multiplied by ال t اللي هي ال mg divided by cosine theta multiplied by sine theta, right? So هيدي هي عبارة عن ال r وهي equation هي عبارة عن ال t. جبناها من equation number 2. And so we can write down now v squared equals to m and m they cancel out. So we end up with l times g times sine squared theta divided by cosine theta. This is v squared. And so we can write down that v is equal to square root of this expression. نرجع للشيء الأساسي اللي احنا بدنا ندور عليه كان اللي هو L is equal to R times M times V. So let's write down then L is equal to R M V. So it's equal to ال R هي عبارة عن L sin theta times M times square root of L G sin squared theta over cosine theta. طيب نحن بالايكويشن الاساسيه اللي كان مطلوب مننا نبرهنها كانوا كل البارامترز بقلب السكوير روت، فلازم رح ادخلهم هول لجوا، واذا دخلتهم لجوا هدول 3 terms بصيروا squared بقلب السكوير روت. So this is why we are going to write down is equal to square root of هيدي بتصير ال بتصير l squared، الساين ثيتا بتصير ساين سكويرد ثيتا، والm بتصير m squared مضروبة بال L times G times sine squared theta over cosine theta. And so it's equal to L to the power 3. So it's equal to m squared, خلينا نبلش بالm مثل ما هو أعطانا إياها. So it's m squared times G times L to the power 3 and sine theta to the power 4 divided by cosine theta. And so this is the equation or the expression that we had to show اللي هي إنه L equals square root of m squared times G L to the power 3 sine theta to the power 4 divided by cosine theta. So this is it for this problem. So problem 28 of chapter 11. A cylinder with moment of inertia I1 rotates about a vertical frictionless axle with angular speed omega I. A second cylinder, this one having moment of inertia I2 and initially not rotating, drops onto the first cylinder as shown in this figure. So this is in the initial configuration where you have the cylinder number 1 with moment of inertia I1 rotating already, and the cylinder 2 is at rest but drops onto the first one. The first cylinder was rotating with omega I. And then finally, what happens, because of the friction between the surfaces, the two eventually reach the same angular speed omega f. So in the final configuration, the two disks are kind of glued together and rotate about the axle with the same angular speed omega f. You have to calculate omega f in part A. In part B, you have to show that the kinetic energy of the system decreases in this interaction, and calculate the ratio of the final to the initial rotational energy. So you have to calculate the ratio between K final and K initial, and you have to show that this ratio is smaller than 1, because that means that the kinetic energy of the system has decreased in the interaction. So let's move to the whiteboard. So you can see here in these two figures, so this is the initial configuration where both disks are separate, and only the disk number one, or the cylinder number one, is, sorry, rotating with omega I. And this is the final configuration in which you have the two cylinders stick together and they are moving with the same omega final. So the question was to determine the angular speed in the final configuration, which is omega final. So the question is, how much is omega final? Okay. Now, in order to determine how much is omega final, the best would be to see how much is the angular momentum of this system, because we know that L is equal to I omega. And if we know L and I, we can determine the value of omega, or the expression of omega. But here we are dealing with two configurations, with two moments. The initial time, which we can call it Ti, when the cylinder one was rotating with omega initial and I2 was still not yet rotating, it was at rest, and then it was dropping onto the first one. And then the time T final, when the two were moving and rotating together about the axle with omega F. Now, if you consider the system of the two cylinders plus the axle, this system is isolated, because no external torques act on this system about the axis of rotation. So we can apply the law of conservation of the angular momentum. And so we can say that if we apply the law, so let me write down that because there are no external torques, because no external torques act on the system, which is made of the cylinders plus the axle, the system, about the axis of rotation, the axis of rotation, we can apply the law of conservation of the angular momentum. And so we can say that L is equal to a constant. That means that L at the initial time is equal to the angular momentum at the final time. At the initial time, the angular momentum is defined by, so in the initially, only the cylinder one was rotating. So omega 1 was equal to omega I, and omega 2 was equal to 0. Right? Or we can actually write down this in the following way. So we can write down omega 1 I1 omega 1 initial plus I2 omega 2 initial is equal to I1. Since in the final state both were rotating together, so we can write it down as I1 plus I2 multiplied by omega final, okay? But since in the initial configuration, the cylinder 2 was at rest, then omega 2 was equal to 0. So we can write down I1 omega initial I is equal to I1 plus I2 omega F. And from here, we can deduce finally that omega F was equal to I1 divided by I1 plus I2 multiplied by omega initial. And so this is the answer to the question. This is the omega final we were looking for, okay? That was part A. So that was the question in part A, how much is omega final? Now the question in part B is how much the kinetic energy has decreased during this interaction. And the explicit question is that you have to calculate the ratio of the final to the of the final to the initial kinetic energy of rotation. So you have to calculate the ratio K final over K initial. So for this reason, we have to evaluate both the initial kinetic energy of rotation and the final kinetic energy of rotation. So initially, K initial was equal to half I1 times omega initial squared, because only the cylinder 1 was rotating, while in the final configuration, both were rotating with the same omega. So it's half I1 plus I2 multiplied by omega final squared, right? And so if we replace in this kf omega f by its expression, so we end up with 1 over 2 times I1 plus I2 multiplied by omega final squared. So it's given by I1 squared divided by I1 plus I2 squared multiplied by omega initial squared. And so if we just make the simplifications, then we end up with omega with k final equals I1 squared, so half I1 squared omega initial squared divided by I1 plus I2. Now, let's make the ratio between the final to the kinetic, to the initial kinetic energy. So K final over K initial is given by, so K final, it's 1 over 2, I1 squared omega initial squared divided by, حتى كلها divided by I1 plus I2. وهون بدي اقسم على K initial، so حيطلع معي 1 over 2 K 1 over 2 I1 omega initial squared. All right, so half and half, they cancel out. The omega initial squared in the numerator and the denominator, they cancel out. And we have finally I1 squared مع I1 من تحت بيبقى بس عنا I1 فوق. So we can write down K final over K initial is given by I1 divided by I1 plus I2, which is smaller than 1 and which we had to show. And in this case, شو يعني K final over K initial is smaller than 1؟ يعني K final is smaller than K initial. And so kinetic energy has decreased during this interaction. Okay? So this is it for this problem. So chapter 11, problem 50. A projectile of mass small m moves to the right with the speed vi, as you can see in the figure here. So this is the projectile, particle of mass m moving with vi. The projectile strikes and sticks to the end of a stationary rod of mass capital M of length d, and which is pivoted about a frictionless axle through its center. You have to find the angular speed of the system right after the collision. So once the particle sticks to the rod, both they rotate about the axle passing through the center of the rod with an angular speed omega. So first of all, you have to find this angular speed, and then you have to determine the fractional loss and mechanical energy due to the collision. Note that this collision, it happens in the horizontal plane. So what we see here is happening on a horizontal plane, and this is, you know, we are looking from up. نطلع من فوق عليها شو عم بيصير. So عمليا ما في gravitational potential energy. There is no variation in the gravitational potential energy, and only the kinetic energy is changing or varying during the collision. Let's move to the whiteboard. So what happens is that we have, this is the road, and then at some point when the collision happens, this mass, it sticks to the end of the road, which has a center in here, and then both they rotate through the angular speed, through the axis of rotation, yani passing by O, and then with an angular speed omega. We have to determine what is omega. So if you consider the system of the road plus the projectile and the axle, no external torque act on this system. So because there are no external torques act on the system about the axis of rotation, then we have conservation. The angular momentum of the system is conserved, or we have conservation of the angular momentum. The angular momentum of the system is angular momentum of this system is conserved, and we can write down then L initial is equal to L final. So in other words, Li equal to Lf, where Li is in the initial configuration, يعني just before the collision, and L final is right after the collision. So إذا اعتبرنا إنه هيدي هي ال L أو هيدي ال final configuration، فالinitial configuration كانت لما كان في عنا الرود محلها this is the point O، وكانت البارتيكل just before, right before to touch the road and to stick to it, okay? So we have to determine L initial and L final. We know that the omega, the angular speed omega, it figures out in the final moment. هيدي الانيشال moment, هذيك الفاينل moment. And so let's do it. In the initial state or in the initial configuration, the road هن كانوا قالوا لنا إنه the road is at rest, it's stationary، يعني ما كانت عم تتحرك ولا كانت عم تعمل أي motion. سواء كان translation أو غير كمان rotation أو غير rotation. So this is why we can say that L initial هي فينا نقسمها لل L of the mass, L of the projectile initial plus L of the road initial. بس ما إنه ال الroad كان stationary، فال road initial was equal to 0، هي عبارة عن L للprojectile initial. Okay. Now how much is L of the projectile? L of the projectile in the initial state was given by R of the projectile vector product P, the linear momentum of the projectile. So it's given by, I'll just call it R for the moment. هي عبارة عن R multiplied by the mass of the projectile times V of the projectile, we can't اسمها VI, okay, multiplied by sine of the angle between the two, okay? So let's now determine how much is the angle. طيب احنا قلنا هيدي هي الانيشال configuration. In this initial configuration البالت او عفوا البروجكتايل كانت ماشيه ب V بهالشكل هيدا. So this is VI in this direction, right? ومباشرة قبل الكوليجن we can actually say انه الفيكتور هو بهالشكل هيدا، هو الفيكتور R, right? So the vector R كقيمة هو عبارة عن نص الرود، right? وكدايركشن هو upward. And so we can clearly say that the angle between R and VI is nothing else than pi over 2 لأنه هن perpendicular على بعضهم، لأنه البول كانت ماشية بشكل with V is horizontal along the X axis بينما R كانت along the Y axis. So we can write down R هي قلنا D over 2، فإذا multiplied by M multiplied by VI علما إنه sin pi over 2 هي 1. Right, and so in this case we are just dealing with the magnitude of this vector. So this is L initial. Now what concerns L final شو عم بيصير عنا؟ بال L final we have a system of particles مبدئيا في عنا rigid body وفي عنا معه particle. They are both rotating about the axis passing through O with an angular speed omega. And so if we have a rotating rigid body, then we know that the angular momentum is given by I multiplied by omega. Okay, now omega, it's the unknown that we are looking for, but how much is I? I is given by I of the road plus I of the projectile, I of the road multiplied by omega. I للprojectile, الprojectile هي عبارة عن particle, right? So you know all by now what is the moment of inertia of the particle? It's given by the mass of the particle اللي هي small m multiplied by the distance between the particle and the axis of rotation to the power 2. The distance ما بين البارتيكل ما بين axis of rotation إذا عم يبرم هيدا السيستم فديستنس بيناتهم هي عبارة عن d divided by 2. And so we have to replace this d over 2 by its value بالexpression. So we replace m multiplied by d over 2, we replace r by d over 2 بنحطها squared plus I of the road. هون في عنا a road which is rotating about the axis passing through its center. So passing through its center of mass. وبنعرف إنه moment of inertia of a road with respect to its center of mass is given by 1 over 12 the mass of the road اللي بهالحالة capital M و multiplied by the length of the road اللي بهالحالة D squared. This is the moment of inertia of our system multiplied by omega. Okay, now just let us make the summation. So we end up with d squared in common factor بتطلع لبرا. So we end up with d squared, or sorry, we end up with m over 4, m divided by 4 plus capital M divided by 12 with d squared بنحطها in common factor multiplied by omega, right? And so if we take 12 as a common denominator, then we end up with m plus 3m divided by 12, all of that multiplied by d squared multiplied by omega. So this is it. All what we need to do now is to just use this law of conservation of the linear momentum. L initial equals L final. That gives us, so m times vi times d over 2 is equal to m plus 3m divided by 12 multiplied by d squared multiplied by omega. And so now if we just make some simplification, d squared بتروح مع ال d. طبعا الان ما فينا نتخلص منه، بقي ما تبقى ما فينا نتخلص منه، فينا بس ان هون we can reduce the factor 2 هون بتصير 6. And so we end up with m times vi is equal to, so m times vi is given by m plus 3m over 6 multiplied by d multiplied by omega. And so finally omega is equal to 6m times vi divided by m plus 3m multiplied by d. And so finally, this is the answer. The angular momentum of the system after the collision, right after the collision, is given by 6m times vi divided by mass of the road plus 3 times mass of the projectile multiplied by the length of the road d. So this was the first question. Now the second question is, you have to determine the fractional loss in mechanical energy due to the collision. So how much is delta E over E? We can call in part P. So what is delta E M over EM? This is how we can calculate a fractional loss. يعني قد ايه عم يصير في تغير بالنسبة ل initial value of the mechanical energy. So since here we are not dealing with the gravitational potential energy in the sense that the variation with respect to the gravitational potential energy is 0, then we're not going to determine this, but we are going to determine the variation in the kinetic energy with respect to its initial value. Yani we are going to determine the fractional loss and the kinetic energy due to the collision. And for this reason, we will need to determine both K final and K initial. So this is equal to K final minus K initial divided by K initial. And let's go on. So بالنسبة للinitial state, in the initial configuration, only the projectile was moving and the road was stationary. So the kinetic energy of the projectile was a kinetic energy for translation, and it's given by 1 over 2 times m times v squared, and v was vi, so 1 over 2 m vi squared. And in the final state, the system was rotating about a given axis. So we have a rotational kinetic energy, which is defined by half I omega squared. احنا الاي already جبناها قبل، طلعت معنا هي عبارة عن m plus 3m divided by 12 times d squared. So رح حتى بقيمتها تحت حيطلع عندنا، فإذا 1 over 2 multiplied by I هي m plus 3m divided by 12 multiplied by d squared, which was we have actually derived this in the previous part, multiplied by الأوميجا squared هيها موجودة هون الأوميجا بس بدنا نرفعها squared, so بيطلع معنا 36m squared v I squared v initial squared divided by m plus 3m squared multiplied by d squared. And so now all what we need to do is some simplifications. فإذا d squared مع d squared cancel out. m plus 3m مع 1 of this m plus 3m squared يعني بيبقى عندنا بس m plus 3m كمان they cancel out. and we still have some numerical factor اللي هو to cancel out اللي هن 36 over, so we end up with 36 over 24, 2 times 12 هي 24, right? Multiplied by m squared v initial squared divided by m plus 3m. Right? So now what we need to determine who is delta k, and then we have to divide delta k by k initial. So delta k, it's given by k final minus k initial. So it's equal to 36 over 24 m squared vi squared over m plus 3m minus half m vi squared. And so if we get the in common, if we take something in common factor, أو خلينا ناخد 2 m plus 3m, right? هيدي 36 over 2 yeah 36 over 2 فينا نختزل من فوق ومن تحت divided by 8 بيطلع معنا 3 over 2. So let me just write down. Or let us actually reduce by 12. بيطلع معنا بتصير 3 over 2 m squared v initial squared divided by m plus 3m. So هون بصير في عنا 3 over 2 بدل ما يكون في عنا 36 over 25, 3 over 2 m squared vi squared over m plus 3m minus half m vi squared. And so let me take the half m vi squared لبرا, فبيطلع معنا هون half times m times vi squared factor. هون بيطلع عنا 3m divided by m plus 3m minus 1. و 3m هون بصير في عنا هي عبارة عن, so it's equal to minus m vi squared over 2. So in order to determine the loss, the fractional loss, لازم نقسم الدلتا k على الk initial. بس هون النيجاتيف sign ما بيفيدنا بشيء. So this is why we're going to take the absolute value of delta k divided by k initial. And so we will write down that is equal to m divided by 2 multiplied, sorry. So here we have still a factor that's missing. اللي هي 2 multiplied by m plus 3m. So بنقسمهم على بعضهم بيطلع معنا plus m times v initial squared divided by 2m plus 3m. And then هون رح نقسم على k initial. So we end up with 1 over 1/2 m v initial squared. Make some simplifications. So m and m cancel out. Vi squared and vi squared, they cancel out. And 2, 1 over 2 also they cancel out. So we end up finally with m divided by m plus 3m. And so this is the fractional loss in the kinetic energy in this reaction, in this interaction, or in this collision coming ما بين الرود وما بين البروجكتايل. This is it for this problem. So a puck of mass m is attached to a cord passing through a small hole in a frictionless horizontal surface. The puck is initially orbiting with speed vi in a circle of radius rr. The cord is then slowly pulled from below, decreasing the radius of the circle to r. So here is the our puck, which is of mass m. Originally, it was rotating about the point, which is through the hole, with radius ri for the circle and with speed vi. Now, after this string was slowly pulled down, the radius of the circle along which this m was moving is not any longer ri, but it's r. The question is, what is the speed of the puck when the radius is r? del v لما صارت عم تبرم على circle of radius r. Find the tension in the cord as a function of r. How much work w is done in moving m from ri to r. Note the tension depends on r. In part D, you have to apply, just to make numerical application, for different values of V, T, and W. So when R is equal to 0.1 meter, mass equal 50 grams, Ri 0.3 meter, and Vi equals 1.5 meters per second. And so here's the figure. So let's move now to the whiteboard. So هي الرسمة. هذه هي ال M. This is the block of mass M. And originally, it was at Ri, and then moving with the speed, which I will just draw tangent على circular path اللي هي كانت VI. Okay? Now the question is, قد ايه بتصير ال V إذا كنا نزلنا نحن من تحت الكورد، وبالتالي صارت الباك تبرم على circle of smaller radius اللي هو radius R. فإذا نحن عم ننتقل من هيدي السيتويشن لما كانت عم تبرم on a radius on a circle of radius Ri and with the speed Vi لحد ما صارت عم تبرم على a circle of radius R and with the speed V. Okay. What happens between these two situations؟ اللي صار إنه كان في عنا force F كانت عم بتشد هيدي الماس بهالاتجاه هيدا. So this is the tension. طبعا هذا اللي عم نشوفه الرسمة هي بالhorizontal plane. So if you look at the pack of mass M, the only external force which was acting on it هي tension T. بحكم إنه ال mg وال n on the horizontal surface they balance each other. This is the only force that possibly would produce a torque. Now let's see if this is the case. In principle, no, because the tension T may be the axis of rotation through which the point M, is making a rotation. But still, let's see how much is the torque of this force. So we know that the torque of the force T is given by the R cross T, right? And so it is given by R multiplied, so this is the R multiplied by the magnitude of the tension multiplied by sine of the angle between the two. Now إذا كنتوا ترسموا الانجل between the two شو في عندكم أنتم؟ طيب أول شيء كيف هو الR عموما؟ It's directed from the center towards the particle, so it has this direction. هاي هي direction للR. Okay. والدايركشن للتي باتجاهها معناتها انه الانجل بيناتهم هي عباره عن باي. Right? So here this is the R. هي الار اللي رسمناها والتي هي بعكسها. يعني عمليا بدل ما احط التي هون التي هي بهالاتجاه بعكس اتجاهها. So the angle بيناتهم هو عباره عن angle pi. And since sine pi is equal to 0, then the torque of the tension is equal to 0. And so we can say that we have conservation of the angular momentum. So we can say that the angular momentum of particle M, momentum of M is conserved. And if the angular momentum is conserved, that means that L initial is equal to L final. Now, how much is L initial? L initial هي equal it's the angular momentum of the mass M اللي هي عبارة عن M times or Ri multiplied by linear momentum اللي هي MVI multiplied by the sine of the angle between the two. بما انه ال V هي على طول perpendicular على ال R فاذا عم نحكي عن pi over 2. وبالفاينل situation كمان هي عبارة عن R multiplied by MV لانه هلا بالفاينل configuration صارت الباك M عم تبرم على circle of radius R with a speed V multiplied by sine of the angle between V and R اللي هو كمان نفس الشيء لانه حتى اذا كانت عم تبرم على circle of radius smaller than Ri بالنتيجه ال V بعدها tangent على هالcircle. So sine pi over 2 of course is equal to 1 everywhere. We can get rid of the mass term هون اللي هو M and M. And so finally we end up with V equals Ri multiplied by Vi divided by R. And so this is the solution to the first question. Okay? Now, that was the first question. The second question is, how much is the tension in the cord? This was the question number 2. Find the tension in the cord as a function of R. Okay. Let's have a look at the figure again. So the tension here is the force that produces the centripetal acceleration. and centripetal acceleration is equal to v squared over r, and v is a function of r. So that sounds great. Let's apply Newton's second law on the block M, and then project it along the radial direction. So we end up with, sorry. So let's apply in part B. Apply a Newton's second law on the block M, and let's also at the same time make the projection onto the radial direction. So بيطلع معنا sum over of Fr is equal to M times AR. The only force that is making an action in the centripetal direction or radial direction هي عبارة عن tension. So we end up with T equals M times AR هي عبارة عن V squared divided by R. Right? So V squared مثل ما شفنا فوق هي عبارة عن RI VI over R. So هي عبارة عن RI VI over R كلها squared multiplied by 1 over R multiplied by M over R. بعد ما حطيت الفactor M over R. And so we can deduce that T has the expression M RI squared VI squared divided by R to the power 3. And so this is the answer to the second question about the tension in the cord. The final question, or the third question here, a final, which the last but one. How much work W is done in moving the mass M from Ri to R? Okay. قد ايه كان الورك needed لحتى نحرك الار لحتى نحرك الام من هيدا الانيشال سيركل للسيركل الجواني اللي هو هون. So this is the question. So the easiest way to calculate this work is to consider the work kinetic energy theorem. Under the action of this force T, under the action of the tension, there was only variation in the kinetic energy in the system because there is no variation in potential energy, for example. Only what changed in the system was the speed of the puck when moving from the initial position to the final position with respect to the axis of rotation of the point اللي هو السنتر للcircle. فبالتالي we can actually say that W is nothing else than delta K, and so it's nothing else than K final minus K initial. Now, initially there was بالK final احنا في عنا ال V وال VI. So let's apply the translational expression for the kinetic energy. هي half M بالfinal هي half mv squared minus half mv initial squared. So we can write down then half m times v squared هي حتكون ri vi over r. So ri squared vi squared divided by r squared minus half mvi squared. So if we take half mvr squared as a common factor هيطلع معنا half mvi squared مضروبة ب ri squared over r squared minus 1. And so we end up with this expression for the work done by the tension during this motion. So this is the result that we are looking for. It's half mvi squared times ri squared over r squared minus 1. And the final question, we are requested to do the numerical application to get the values for V, T, and W. And so finally, let's do it in the part D. If we take the numerical values for R, N, Ri, and Vi, we end up with, first of all, V, اللي كانت Ri times Vi over R حتطلع معكم 4.5 meters per second. Then you end up with T as given by 10.1 Newton, and you end up with W equals 0.45 Joule. And so this is it for the numerical applications. And this is it for this problem.